Questions about anything from last time? I'll say a few words about that proof. I cleaned it up when I posted the notes. I fixed a couple of things that I failed to mention. And that explains why Drew was asking some questions. I fumbled up the notation a little bit. So I'll explain how I fixed that. Anyway, today is the last material. Fridays for review, I'll go over the practice problems. And I've now posted hints for the practice problems, which should make some of them more doable for you. Those practice problems were meant to be a learning experience, so they're kind of too hard for an exam question, but they certainly will help you review the material and understand it better. So once again, I've chosen them to be educational. The old exam is a good thing to look at for this level of difficulty of a typical final. Nobody expects you to get a perfect paper, but certainly some of the problems are easier than others. And sometimes one of the problems is harder than I expected. And it's like it wasn't even there if nobody gets it right. So don't freak out if you see something like that. Anyway, so today's, I need to remark about last time. I did the general residue theorem for a meromorphic function, which only has poles at a discrete set in a domain. Well, if you look at the proof, it doesn't use the fact that they're poles instead of essential singularities. So the general residue theorem that I stated last time, the statement works exactly the same, and the proof is exactly the same if F is allowed to have essential singularities in addition to poles on a discrete subset. So that's just a remark to be aware of. Any questions about last time? So let me pull up the proof from last time and look at it. So the general residue theorem was about, I said F is meromorphic, but it could have essential singularities, so that would be okay. And I've got a domain, omega, and a cycle that's homologous to 0 in omega. And F has no poles on the trace of that cycle. Then the new residue theorem is that the integral around that cycle of f dz is 2 pi I times the sum of the residues, but they're weighted now by the index with respect to each of the points in that discrete set. And I did remark that that's a finite sum because the set where the index is not 0 is a compact set when you toss in the curve itself, and if there were infinitely many in there, they'd have to have a limit point. And of course, it's a discrete set. Discrete sets don't have limit points in omega. So there's only finitely many points in the discrete set. So I called the set where that index was not 0 in among the poles, singularities, I call that German A. Okay. And so the idea of this thing is to add some curves to the cycle and change the domain by punching out those singular points. And applying the Cauchy theorem to the new domain with the new cycle. All right, and so I define this going around the little circle nj times by that notation there. We're going to add a bunch of little circles, finitely many little circles to our cycle, so it becomes homologous to 0. So this is why the essential singularity thing works. When I had a pole, then this integral of f around the little circle is 2 pi I times the residue. If it's a pole, well, that's true if it's an essential singularity too. That was the definition of the a minus 1 term in the Laurent expansion. So that part would still be true. That's the only thing that changes if that was an essential singularity. It doesn't change. Okay, so I let German A be the set of singularities where the index was not 0, and that's a finite set. And then I took little disks about each of the points in that A, and I shrink them down so they're all so small that they don't get near each other, they don't get near the cycle, and they're disjoints, yeah. Okay. And I make a new domain where I punch out the points in the discrete set. I actually should have said that I was punching out all the points in the discrete set. The ones where the index are 0, we don't really care about, but I need to punch them out. So step 1 should be to remove all of the points in the discrete set. And so we only have to worry about the ones where the index is not 0. Okay, so we're going to take a new curve where we add to our cycle a bunch of these little circles that go around in just the right number of times so that the index is going to be 0 with respect to those points in German A. So the thing I didn't have last time was step 1 is to remove all the points A in the A's from omega. Okay, so there's the picture. If that's the cycle, if the green stuff is the cycle gamma, then I'm adding these little circles to cancel out when I add up all the indices at the A's. And the interesting thing is that that doesn't change the fact that the thing is homologous to 0 for the other points. It only makes it true for these new points that we have to worry about. All right, and so in my remark that Drew was asking about, I was using A for two things here. A was supposed to be a point outside the domain. And I also used it as the points in my index set. So now I fixed it here. A is now a point outside the domain, and I fixed these to be AJs. These are the finitely many points in the German A set. Okay, now that would make more sense, and I understand now what Drew was asking me about. Anyway, that proof is fixed now. It's not a hard thing. It's just hard to. It's hard for me to say it in words. The picture says it all. Okay, so that, and I fixed that when I posted these notes on the homepage. Questions about it? Okay, well, today's material is Mittag-Leffler theorem. Mittag-Leffler was a single person, Swedish mathematician. And the Weierstrass theorem. The Mittag-Leffler theorem is about prescribing poles. And Mittag-Leffler did the case of the whole complex plane. But it's also true for any old domain that you can prescribe poles sort of however you want. So the theorem is, let's suppose I've got a sequence of points in the complex plane, an. They're distinct points, so not repeated. And they go to infinity as n goes to infinity. All right? The Mittag-Leffler problem is to construct a meromorphic function on the whole complex plane that has poles exactly at the an's. And only that, but you can prescribe the principal parts. So give yourself a bunch of principal parts at the an's, like that. There exists a meromorphic function on the whole complex plane with poles at exactly the an's, having the principal part that was specified at an for each n. Okay, that's going to turn out to be rather easy to do, and it's the first Mittag-Leffler argument. I'll explain what that means. The Weierstrass theorem is about prescribing zeros. So if I give you positive integers mn for each an, there exists an entire function with zeros of order mn at the an and no other zeros. So you can prescribe zeros too. And a corollary of those two theorems let's see what's the corollary is that the meromorphic functions on the whole complex plane are equal to, it's a division ring, so it's F over G, such that F and G are entire, and G is not identically 0. So the meromorphic functions are the division ring you get from from entire functions. That's kind of a cool thing to know. Let's see, why would that be? I guess the proof of the corollary is easy. Proof of the corollary. Let's see. Suppose that you have a meromorphic function f with poles at the a ends. Of course, the a ends are discrete, so if there's infinitely many poles at the a ends of order n, or let's call it mn. Then Weierstrass implies you can get a G that has it implies there exists an entire G with zeros at those poles. With zeros of order mn at an. Now, f, which should be equal to our original meromorphic function times g, those zeros would cancel the poles. Has removable singularities at the an. Because the zeros cancel the poles. And so, of course, the capital F is F divided by G. So the two things, when you put them together like that, spit out that sort of natural fact to understand. Okay. Well, let me do the proof for the Mittag-Leffler. It turns out to be rather straightforward. So here is the proof of the Mittag-Leffler theorem first. Here's the trick. Let's try let f, you'd like to say, I can just add up these principal parts. But there's no reason those would converge. They do, as the an's go to infinity, those rn's get small, but it's not clear they get small fast enough to be able to add them up. Sometimes you can. Sometimes that gives you a solution. Sometimes it doesn't. But Mittag-Leffler's brilliant idea was to make a correction here so that these things would converge, and these things here are going to be polynomials. Where let's see, Pn of z is the Taylor polynomial. You get Taylor polynomial for Rnz about z equals 0. Such that we want Rn of z minus the Taylor polynomial to be less than 1 over 2 to the n, so really small. The sum of 1 over 2 to the n converges, so I'm going to use the Weierstrass M test. Let's see, you can't have that everywhere because Rn has poles, but we can have it on a disk of radius Rn about 0. Let's make it on the closure, why not? Where remember, power series converge uniformly on compact subsets, so that's within, we'd have a uniform convergence on that, and I can make it less than 1 over 2 to the n, where Rn is the modulus of an divided by 2. The pole is at an, so that would be, Rn would be analytic in there, and I could get uniform convergence on that smaller disk. Well, the claim is that this F works. F solves the Mittag-Leffler problem. And so let's see, the proof is going to be a snap. Let's take a big R. Think of it as a big one. Take a big disk, dr about 0. I want to show this thing converges on that big disk. Well, let's see, there exists an n such that Rn, remember, Rn was the modulus of an, which is going to infinity over 2. So that there exists an capital N, so that's bigger than my big R, if n is bigger than n. And now if you think of what F is, F of z, first I'll take the beginning terms. That's the sum as n goes from 1 to capital N of a rational function, which is the principal part, minus polynomials, and then the rest of the junk. Okay, this thing, this would be n plus 1 to infinity, and then we'd have, I'll write it again, Rn of z minus Pn of z. So I'm going to look at on this disk of radius r about 0. I'd write this. This is a rational function, and it has the proper principal parts. Rational function with prescribed principal parts, at least inside that disk. Okay, so that part's, and it's a finite sum. So it is a genuine rational function. Okay. This part is where I can use the estimate, because the RNs now would be bigger than this, and so I'd get the I would get the estimate, namely that the modulus of Rn minus Pn is less than 1 over 2 to the n on dr0. And so the Weierstrass M test tells me that that converges uniformly to an analytic function. Weierstrass M test implies that sum converges to an analytic function uniformly. To an analytic function on the disk of radius r about 0. Okay, so F is the principal part plus an analytic thing. And that's, remember, that was the characterizing feature of a principal part. When you subtract off the principal part locally, what's left is an analytic function. So f of z would be equal to Rn of z plus analytic function near an in the disk. Of course, ours could be made arbitrarily large, so that's true for all of them. Questions about that? That's a really clever argument. So the Mittag-Leffler argument is when you make corrections that are small, and even so small that when you add them up, they're still small, and get what you want. So you correct it by adding another analytic function, basically. That's a clever argument, though. And it comes up in analysis a lot. I use it in PDE in some of my work in a PDE context. I guess I should make a remark that the Mittag-Leffler theorem is true not just for C, but for any domain. For a discrete A in any domain, I can cook up a meromorphic function that has prescribed poles on the discrete set. I can cook up meromorphic function with prescribed poles. And it can even have holes. Okay, but that would require more advanced tools. I like to solve that problem solving the Cauchy-Riemann equation, so it's a PDE problem for me. Okay, that's the Mittag-Leffler theorem. Now let's do the proof of the Weierstrass theorem. Questions about that proof? I'm going to cook up zeros now. Well, let's see. This is not a proof you'll find in many books. So my proof is going to be the Mittag-Leffler theorem plus the general residue theorem implies the Weierstrass theorem. Weierstrass himself used infinite products in a very clever way. It's a beautiful thing to see. In fact, it's so beautiful, that's why that's the proof that's in all the books. But I haven't done anything with the general residue theorem yet, so I want to do this because I like it. So let me think out loud for a second here. If I had such an f, then I know that f prime of f, remember that was the argument principle thing, it would be the order of the zero would be the residue at z minus an, plus something that's analytic. This is a simple pole, and the residue is the order of the zero. Okay, that's something to think about. And I think about the Mittag-Leffler theorem implies there exists a function with those principal parts. With poles at the ANs, exactly those principals parts. With poles at ANs, with principal parts, what we would expect. Mn over z minus an. Okay, so that's one thinking out loud thing. And then another thing to think of is when we were constructing various things. We could write f of z equals, this is an equals with quotes, e to some branch of log of f. And when we were constructing these things, we wrote those branches as an integral from a to fixed point a to z of f prime over f. Okay, so those are the two big ideas. Sorry. Okay, so now here's the details. Mittag-Leffler theorem implies there exists a meromorphic f on the whole complex plane with those prescribed poles, with poles at the a ends. With principal parts, what they're supposed to be. Order of the 0 divided by z minus an. What the heck? Okay, now I'm going to say define in quotes. F of z is going to be that thing I wrote there. Let me cheat. Where, let's see, that gamma is a curve. Gamma AZ is a curve. Let's see, it shouldn't go over any of the ANs, so it's going to be a curve in C minus the ANs, starting at a fixed point A that's also in that set. So a fixed point, which is fixed for all time now, point A in the set, and ending at z. Well, step one is to see this is well defined. And this is where I'm going to use the residue theorem. So step one, even though it looks like it might be questionable, f of z is well defined. And that's once you have that, then the rest just falls out. Okay, let's think about that. What if let's see, so I do this. Sometimes I would take a minus here, but since it's an exponential of something, it's not 0. So I can take, if I want to show that it's the same, if I take an f of z that I define one way, and an f twiddle, which I define using a different curve, that would be exp divided by exp. And of course, the exponential satisfies the great property that this would be the exponential of let's see, the f would be the integral from gamma with no twiddle. And then the f twiddle would be using the gamma with a twiddle, a different gamma perhaps. And we do f prime over f. So some of the homework problems where I give you hints, you're going to be doing this sort of trick. And when you think about this now, this is a closed curve. So I would take gamma to be equal to go out by one and go back by the other. Is a closed curve. And of course it doesn't go through any of the poles. And now for the first time I can use my general residue theorem. So that's a closed curve, and by the the general residue theorem on the complex plane would be that that's equal to the exponential of 2 pi I times the sum of the the index comes in here, index gamma. The good news is that's an integer, and then the residue at an of my meromorphic function f. Did I say? Okay, so here's what I meant to put here. I meant capital F's here, sorry. Capital F. F is well defined. So this didn't make any sense. These are the functions I got from Mittag-Leffler. Capital F over F. Sorry about that. My little f is different than that capital F. And if you think about that, this thing is an integer. This thing is also an integer, mn. And so I get exponential of 2 pi I times an integer. And by the way, this is a finite sum because only finitely many of those could be non-zero. And so this is e to the 2 pi I times an integer to the n times 2 pi I. Not n, but something. K. K, an integer. So that's a big fat 1. It's actually it could be a negative. The index could be negative, so it could be a negative integer. So that's a big fat 1. And so those those f and f twiddle are the same. Questions about that? That's a fantastic argument. When you realize you can do something like that, you see how powerful the general residue theorem is. So f of z is equal to f twiddle of z is independent of the choice of curve. As long as you stay away from the poles. Okay, now the rest is going to be somewhat familiar. Step 2, now that we know what f is well defined, the easy thing is to see that f is analytic on C minus the poles. Okay, and we've sort of seen this trick before. I would restrict my attention to a disk, and I can make it as small as I want. The center of that disk would be a z naught maybe. And then I would take my one curve. Now that I know it's independent of the choice, I take my curve going, starting at A and going to z naught first. And let's see, there's some ANs would be around here maybe. But I'm missing the ANs. And this is a small enough disk that there's no ANs in it. And then I would take, for the rest of the way, I would take the line that goes to Z. Then, of course, I can write f of z is the exponential of, first I would integrate from A to Z naught. That's a constant. plus the integral of the line that starts at z naught and goes to z of f prime over f. And we know that's an antiderivative. So this thing is a constant. This thing is an antiderivative for the thing inside. On the disk, the little blue disk. And if I cared to compute it, let's see what I get. Yeah. So that's analytic. So we just see it's analytic. If I wanted to compute the derivative, I could at this point. It'd be a constant times something. So, but I don't really care what that is. It's analytic on the disk. Okay. Now I'm going to show you that the next step is that AN is a removable singularity. And in fact, it's a 0 of order n. And is in fact a 0 of order mn. And so we'll be done. Let me give you another picture. Proof. It's actually going to be easy. So now my point that I'm under consideration is a pole, one of the pole things. And I'll take a little disk about that. So I can make a small one here so there's no other ANs in there. And now I'm not going to go to the center this time because that's a pole. But I'm going to go to a B here. And it's going to be on the... This is a... It's going to be right there. This is a B. I'm going to start from my A and take my curve over to B. Like that maybe. And here's going to be a branch cut. Let's see. I'll take a branch cut going like that, and I'll go dot, dot, dot. My B is on that same branch cut thing for the principal branch. So this orange thing here is a branch cut for the principal branch, capital LOG of Z minus AN. Okay. And so let's see, this is gamma from A to B, and this is going to be the line that goes from B to Z. Okay, and now the fun part. F of Z is the exponential of, this is a constant. We go from A to B. Let's see, there could be poles here, but we're avoiding them. A constant of F prime over F. I realize I screwed up. My capital F is the thing that has poles. So here's this thing had the poles like as if it was F prime over F. So I should have. This is an F right here. I don't know why I did that. My F has the proper pole to look like an F prime over F. It's not an F prime over F though. It's the Mittag-Leffler function. Okay, so I shouldn't have put F prime over F in there. Shouldn't have it here either. And you'll see why. Okay, at least I put it right there. How many other times did I do it? A couple more. Anyway, I'll double check this when I get back to my office. It's definitely an F. Okay. And the last one, F, dW. Okay, that's a constant. Then I integrate from LB to Z. And now I'll write this as, the first part is Mn over W minus AN, dW. And the rest of it would be an analytic function. So that's the principal part. And so what's left would be an analytic function on that disk. So this thing is analytic on the disk. And this we can calculate. Because I got a branch of log. And let's see, so this would be Mn times the log of Z minus AN minus the log, principal branch of log, of B minus AN. That's a constant. And so the aha moment here is f of z. Let me pull out the part I care about. That would be the exponential of mn times log z minus an times the exponential of an analytic function. When I put the constants and other stuff. That integral, the last integral there, is an antiderivative for that capital H. And the exponential of mn times log is z minus an to the mn. Because the exponential of log is the thing that's inside. That's the definition of log. Not always true that the log of the exponential is what you think it is, because there's choices. But the exp of the log is the thing inside. Okay, and so we see that that f extends continuously past the branch cut. Okay, this is analytic. On the disk and unequal to 0. So it's non-vanishing there. Okay, so we see, and now we realize, remember that there was a theorem that if something is continuous from the, so here's that picture, here's my disk, here's the AN pole right in the middle, and I had this branch cut, and now I've got a function that is analytic on the top of that branch cut, analytic on the bottom, and they extend continuously and agree there. So we have a function, analytic, above and below the cut, and extension to the cut is continuous, and they agree. So it extends continuously to cut. That's where I use the Morera theorem to show that f is actually analytic across the cut. the Morera trick argument that I showed you before implies the cut is removable. Well, actually, that's the thing. There's a formula, and that formula is valid away from the cut, and nothing bad happens at the cut. It doesn't blow up. It doesn't do anything. So, of course, it extends past the cut, and that's the formula for it. I think that's a fun proof, and I don't understand why it's not in the books, because it demonstrates the usefulness of the general residue theorem. But I wish I had time to show you infinite products, because they're beautiful. And if you're going to study number theory or something like that, Weierstrass used infinite products of analytic functions to make functions with zeros. And there's things called Weierstrass polynomials that he used that were very clever. And it's beautiful math, and it's very useful when you're if you're going to do number theory and that kind of thing. So you might want to read it in Stein. I'll post some. Usually I manage to squeeze in one more lecture before I review, where I blast through infinite products just so you know the words. Anyway, I'll post some notes about it so you at least see the words. Probably all running out of steam, so save it for something when your strength comes back. Anyway, it's good stuff. So Friday is a review, so if you have time to look over the practice problems, now that you've got my hints, you won't run into any brick walls like you might have the first time you looked at them. I did that on purpose so you could have a chance to enjoy the brick wall. It would be educational. But with the hints, I think you could get over any of those brick walls. Especially after you saw this lecture today, because there's at least two that use this very similar idea. Any last minute questions? Yeah.
I have a quick question. So above in the proof where we broke up F, if you can scroll up slightly, I think there's a part where, right there. How do we know we can break up F into this mn over w minus a?
Well, let's see. The function was capital F. And so that capital F had the principal part, mn over w minus an, and therefore that's the principal part, so the rest would be an analytic function, which I'm calling h.
Okay, so we started off with the principal parts being the mn.
We prescribed the principal parts and solved the Mittag-Leffler problem to get a meromorphic function with those principal parts.
Perfect. Okay.
Yeah, and so those two sort of motivating things lead to something that works beautifully. Like this. Yeah. Other questions? So I might have an office hour on Monday if I feel good enough after my root canal. So I'll send an email if I'm going to have it. But otherwise, if you need me, maybe Piazza or email works. Okay. See you Friday.